Today, we are diving into a puzzle so complex, it's pretty much impossible for even the most brilliant chemical engineers to solve on their own. And we're going to see how a very special kind of AI cracks it by thinking like one of them.
Okay, to get a feel for this, just imagine you're staring at a giant, messy pile of Legos. Your job? Sort them all by color, shape, and size, all at the same time, to figure out the absolute most efficient way to build something. That, in a nutshell, is what we're talking about with separating complex chemical mixtures.
And the scale of this problem is, well, it's just staggering. For a mixture with only 10 components, using just 2 different separation methods, you're looking at nearly 10 million possible ways to do it. There's just no way you could guess your way to the best one. The numbers are way too big for any person to handle.
So yeah, it's no surprise that in the world of chemical engineering, this is known as an impossible puzzle.
The official name for this headache is separation sequencing. And look, it's not just about getting the chemicals apart. It's about finding that one perfect sequence, the most efficient, the most economical, out of literally millions or sometimes even billions of other ways you could do it.
So if just throwing more computing power at it, brute forcing the answer, isn't going to work, how in the world do you solve it? Well, the key isn't more power. It's about thinking differently. It's about thinking like an expert. And this is where our hero, an expert system called EXSEP, enters the picture. Now, EXSEP doesn't try to check every single possibility. No way. Instead, it's built to use rules of thumb, these little shortcuts and bits of wisdom, exactly like a seasoned engineer would.
And these rules of thumb actually have a technical name. They're called heuristics. You can just think of them as mental shortcuts. They're the things that experts learn over years and years of experience that let them make really good decisions fast without having to start from scratch every single time.
But here's the tricky part. Sometimes that expert wisdom can actually contradict itself, right? Like you might have one rule that says, hey, always remove the most plentiful component first. But another trusted rule says, perform the really difficult separations last. So what do you do when your most plentiful component is also the hardest one to separate? Which rule do you follow?
The solution is actually so simple, it's beautiful. It's called a rank-ordered method. Exsep has a strict list of its rules, ranked from most to least important. It just goes down the list one by one. If a rule applies, great. If it doesn't, it just shrugs and moves on to the next one. No conflict, no confusion. Problem solved.
All right, so how does this whole thing actually work in practice? Let's take a peek inside Exsep's Smart Toolkit and see how it actually thinks.
So first, to even see the problem, the AI lays everything out in something called a Component Assignment Matrix, or CAM for short. It's basically just a simple grid, a map. It shows how much of each chemical, like our A, B, and C here, needs to end up in each final product.
Once it has that map, its thought process is incredibly logical. First, it maps the whole problem out using the CAM. Then, and this is crucial, it asks, is this split even possible? And if the answer is yes, then it moves to the final step, choosing the right rule, the right heuristic from its ranked list.
Right, but hold on. How does it know if a split is feasible without running some massive, time-consuming simulation?
It has another clever trick up its sleeve. It uses a shortcut analysis. This is just a quick and dirty check to see if a separation is even possible according to the laws of physics. And, just as important, if it makes any economic sense. This lets it immediately spot and avoid dead ends that would waste a ton of time and money.
So let's talk about these rules. What exactly is in EXSEP's playbook? Let's look at a couple of the heavy hitters.
One of the most important heuristics is to save the hard stuff for last. The logic here is just common sense, right? You want to simplify the mixture with the easy splits first. That way you're dealing with way less material when it's time to tackle the really tough, energy-intensive part. And here's that other big one we mentioned. Remove the most plentiful component first. Again, super logical. If you can get the biggest piece of the puzzle out of the way early, you dramatically reduce the workload for all the steps that come after. That's a huge energy saver. And Exsep's whole strategy guide is packed with this kind of expert wisdom. Stick to common methods like distillation. Avoid extreme cold or vacuums because they're expensive. Get dangerous stuff out of there first. All of this is basically decades of human experience, all encoded into the system.
Okay, before we wrap up, I have to show you one last really clever cost-saving trick that this system uses.
It's a technique called stream bypass, and it's kind of wild. The idea is, instead of sending 100% of your chemical mix through a separator, you just send a portion of it around, skipping that step completely.
Now, the obvious benefit here is saving money. A lot of money. If you're processing less stuff, you're using less energy, and you can get by with smaller, cheaper equipment. It cuts down your costs right from the start and saves you money every single day it's running.
But here's where it goes from clever to genius. Sometimes, bypassing a stream changes the chemical composition just enough that a separation that was previously impossible suddenly becomes possible. So it's not just saving money, it's literally creating new pathways to a solution that didn't exist before.
So when you boil it all down, the real key here isn't just raw computing power. It's about strategy. To Exsep solves this impossible chemical puzzle because it takes the gut feelings, the intuition, and the hard-won wisdom of a human expert and translates it into a logical, step-by-step process that a computer can follow perfectly every single time.
And that really leaves us with a huge question to think about. If we can solve this problem by teaching a computer how to think like a chemical engineer, what other impossible problems out there are just waiting for us to teach a computer how to think like an expert?